Hey, welcome back to Calculus. In this second video lecture of section 3.6, we're going to take a look at a technique of integration called logarithmic differentiation that can use these logarithm properties that you're looking at, these laws of logarithms, to greatly simplify derivatives of functions, well, that are kind of ratios of products of powers of x. We'll take a look at it in an example. So why start off with these laws of logarithms? Well, because I'm going to use them when I use this technique of logarithmic differentiation. And why are they useful? What this first logarithm property says, for any base, we'll primarily use base e, but for any base, the logarithm of a product is the sum of the logarithms. So imagine if you were trying to differentiate some product, if you applied the logarithm first, you can turn that product into a sum. Sums are easier to differentiate than products. Likewise, differences are easier to differentiate than fractions. Yeah, scalar multiples are easier to differentiate than powers. So these logarithm properties kind of transform things that are a little bit more difficult to differentiate into expressions that are easier to differentiate. Now, the downside is you have to introduce a logarithm to do it. Let's take a look at an example. I'm going to leave these logarithm properties in view. So here's a typical example of something that you'd want to do with logarithmic differentiation. I've got kind of a complicated fraction there. It's got power functions in it that are multiplied. There's a ratio. You could handle this thing with the product rule, power rule, chain rule, quotient rule. There's nothing that would stop us from differentiating this function. But if we use these logarithm properties, we can simplify the computation. So I'm going to start off by taking this expression y and taking its logarithm. I'm going to use the natural logarithm. Technically, you can use any base, but I'll just use the natural logarithm. So I'm going to take the logarithm of this entire expression, x to the 2/3 times x cubed plus 1 to the 1/2 over 3x plus 2 to the 5th. Okay, so that's how the computation is going to start, is I take the logarithm of that thing. But now using those log properties, they're going to scroll out of view here. But what am I going to do? I've got a fraction, yeah? So I'm going to use that second logarithm property. I'm going to rewrite this thing. I'm not going to write all these steps. I'm just going to talk you through them. So looking at this fraction, I'm going to write it as the natural log of its numerator minus the natural log of its denominator. So that's how I'm going to get rid of that fraction. In the numerator, there's a product. So when I take the natural log of that numerator, I'm going to write it as the natural log of this factor plus the natural log of that factor. That's using the first logarithm property. And then in all three summons that are there, I've got exponents. And I'm going to use this last property to write those exponents as coefficients. Right? So the 2/3 will come down, the 1/2 will come down. So if I do all of that, let me scroll a little bit to give myself some room to do it. What am I going to get? Well, I would have this log of x to the 2/3, but that 2/3, pardon me, is going to become an exponent. So I get natural log, or 2/3 natural log of x. That'll come from this factor. Yeah, and then I would add to that, because of the product, 1/2 times the natural log of x cubed plus 1. That comes from this factor. And then subtract, because of the division, 5 times the natural log of 3x plus 2. Yeah, that comes from the bottom factor. The 5 is now the coefficient, and it's a subtraction because that part was in the denominator. All right, so that's just taking the logarithm of that expression using those logarithm properties. Now we differentiate implicitly. Now I'll take the derivative of both sides with respect to x implicitly. So on the left-hand side, well, the derivative of the logarithm is 1 over y times dy dx, chain rule. And on the right-hand side, I just have a bunch of logarithm properties. So, well, or logarithm derivatives, excuse me. So I've got 2/3 times the derivative of the natural log, that's 1 over x. I've got 1/2 times the derivative of log of x cubed plus 1, so that's 1 over x cubed plus 1 times the derivative of x cubed plus 1 by the chain rule. and then 5 times the derivative of log of 3x plus 2, so that's 1 over 3x plus 2 times the derivative of 3x plus 2 by the chain rule, all right? So now the last step is to solve this thing for dy dx. Well, dy dx is equal to y times this expression on the right. Yeah, if you multiply both sides by y, but instead of y, I'm going to write its expression in terms of x. So I'm going to write this expression up here again, x to the 2/3 times x cubed plus 1 to the 1/2. Just writing y, 3x plus 2 to the 5th. And then what's it times? Well, it's times that bracketed expression that starts off 2/3 times 1 over x. So if we just simplify that a little bit as we go, I've got 2 over 3x. And then what would we have? Plus 3x squared over 2 times the quantity x cubed plus 1, minus 5 times 3 is 15 over 3x plus 2. All right, so there you go. There's the derivative dy dx performed logarithmically. Cool. So I hope you'll practice a few of these things. I want to keep this video short, so I'm not going to do too many more examples. I do want to show you this box that I clipped out of your book. I think it's kind of a nice summary talking about when you have, some exponential expression. So you've got some thing that's called the base, and it's raised to something called the exponent. Yeah. And what the author is talking us through here is that there are sort of perhaps easily confused, but you want to get these things down, differentiation rules. So if both that base and that exponent are constant, well, then the exponential expression is a constant, and so its derivative is 0. Yeah, so that's what the author is telling us in this first line. If both the base and the exponent are constant, then the derivative is 0. If the base is variable, but the exponent is a constant, then that's the power rule. Yeah, when the base is what's changing, but the exponent isn't, then you differentiate that with the power rule. And here the author is giving us an inside function that's general, an f of x, so he's writing the general power rule. It's n times f of x to the n minus 1 times f prime. If you go the other way, if the base is constant but the exponent is variable, that's when you have an exponential function. That's when you use this exponential rule. So again, the author is kind of being general in writing g to the x. I know the font is very small there, but b times g to the x, well, it's the derivative of the exponential. That's your b times g to the x times log b. If b is equal to e, then that log b term is just 1 times g prime by the chain rule. All right. So neither of those rules applies if both the variable, the base and the exponent are variable. So if that's the case, then you have to use this logarithmic differentiation technique. So let me show you an example. Scroll up a little bit here. I can unveil my example. So here I've got an exponential expression where both the base, x, and the exponent, square root of x, are variable. Yeah. So I'm going to call this y. Y is x to the root x. And we're going to differentiate this thing logarithmically. So I'm going to take the natural log of y first. Why do that? Well, because by logarithm properties, the natural log of y is the square root of x times the natural log of x. Yeah, because when you take a logarithm of an exponent, that exponent can become a constant. So this thing can literally, or become a constant multiple, becomes a constant multiple, a coefficient. That's what I'm trying to say. My tongue's not working all that well today. So now let's differentiate this thing implicitly. Okay, so the left-hand side, the derivative of logarithm is 1 over times dy dx. Yeah, implicit differentiation. This side we have to do with the product rule. Maybe you want to convert that x, at least mentally, to the square root of x to a 1/2 power. So the product rule is, okay, leave that 1/2 power alone times the derivative of log plus the derivative of the 1/2 power times the log left alone. All right, and that simplifies a little bit. X to the 1/2 times 1 over x is 1 over x to the 1/2. And then what have we got? Well, we'd have a log x in the numerator and a 2x to the 1/2 downstairs. And if you want to get a common denominator, we can write that thing as 2 plus log x all over 2 times, I'm going to go back to the radical notation, square root of x. All right, so that's not equal to dy dx, that's 1 over y times dy dx. So you multiply both sides by y. So dy dx is y, which was our x to the root x, times that thing, 2 plus log x over 2 root x. All right, so there is the derivative of the pretty intimidating looking function x to the square root of x. But the whole point of this, I'm going to scroll, well, let me look at that for a second. The whole point of it is when you have something of the form f of x to the g of x, so both the base and the exponent are variable, then you use logarithmic differentiation to compute y prime. Okay. We're going to end this just with kind of a cool conversation about the number e as a limit. I've tried to convince you that the number e is nice because the exponential, natural exponential, and natural logarithmic functions have the simplest derivatives. But let's take a look at where the number e comes from, and this might remind you of some computations that you've done before with continuous interest, depending on if you looked at applications like that in your pre-calculus class. So I'll just walk you through this real quick. We'll keep it short. So if you take the function f of x equals log x, then its derivative is 1 over x. So in particular, its derivative at x equals 1 is 1 over 1, or 1. All right, so that's just an observation to start with. The derivative of the logarithm function at 1 is 1. So f prime of 1 by the limit definition of derivative is this limit. H goes to 0, f of 1 plus h minus f of 1 over h. And I can switch the name of the variable in that limit. That's all I'm doing here is I'm just calling the variable x instead of h. So that's certainly not going to change the value of the limit. And then down to this line, I'm just kind of reorganizing my algebra. Instead of dividing by x, I'm multiplying by the reciprocal. That's it. And then let's remember that the natural log of 1 is 0. So that thing in the brackets is really just natural log of 1 plus x. And now I'm using that logarithm property again, but this time kind of in reverse. I'm going to take this coefficient and make it an exponent. Yeah, logarithms say that you can do either one. So when I'm done doing that, I've got this thing. I've got that limit, and that's f prime of 1. And let me remind you that f prime of 1 is equal to 1. All right, so then what am I going to do? I'm going to say, okay, well, e, the function of the number, the number e is certainly equal to e to the 1. But 1 is given by this limit expression. So I'm just going to replace, I know it seems like a crazy thing to do, but I'm going to replace the number 1 in that exponent with that limit. Yeah, so because they're equal. But e is a continuous function. So if you're taking e to a limit, you can switch limit and e. Remember, continuous functions and limits can be interchanged. So instead of taking the limit first and then raising it to e, I can raise that expression to e first and then take the limit. And the reason that's nice is over here, I've got an e to the log of something. Well, e and log are inverses of each other, so I just get the something. So if we kind of summarize that on a single line, what have we got here? Let's focus on this thing. I wrote two things, but first of all, e is equal to this limit. The limit as x goes to 0 of 1 plus x over 1 over x. And if we just want to make a little bit of a variable substitution, you don't have to do this, but if you call x 1 over n, well, then x would go to 0 if and only if n goes to infinity. Yeah. If n is getting big, this quantity is getting small, and vice versa. So we have these two kind of limit definitions of e. E is the limit of 1 plus a small number to the reciprocal of that small number as the number gets smaller and smaller. You can even read that like this. E is the limit of 1 plus a small number, right? Because if n is big, 1 over n is small, to the reciprocal of that small number. And this is the form where you may have seen maybe in a continuous interest application, compound interest application, this limit kind of comes up, although you wouldn't maybe have spoken about the limit. So there's kind of a natural way in which the number e arises from the calculus. We'll end this video. I'll just show you a table I took from your book that's illustrating this quantity 1 plus x to the 1 over x. Maybe you could reproduce this table on a spreadsheet. That'd be kind of a fun exercise. If you're still wanting to practice that skill, making a table of values of a function on a spreadsheet, this is a good function to try to input, and then you could make your variable column take on those numbers. It looks like we're getting down to, how many zeros is that? That's 10 to the negative 7th. Yeah, so that's 1 over 10 million. And you can see that it's clear that these numbers are approaching something. They're changing less and less. The second decimal place stopped changing in this row. And then we're at 718, 7182, and so on. So this thing is an approximation for that number e out to, well, it looks like about 7 decimal places. Okay, I'm going to end this video here, so thanks for listening.